Hi, it's Miss Heaton signing in to talk with you about advanced rate law calculations. I'm going to go through one example with you that will hopefully help you understand how to do the more complicated rate law calculations. So what you see here is that this reaction has 3 reactants, which to start out makes it more complicated. So that means when we're finding the exponents, we're going to need to find, like for example, if we wanted to find how the rate depended on the concentration of bromine, we would have to make sure that BrO3- and H+ stayed the same in the 2 experiments that we picked. So let's start by writing our generic rate equation. Rate equals K times Br, our first reactant, to the m power, times BrO3- Bro to the n, times H+. We'll use exponent p for that. We'll skip O because it looks like a 0. So let's compare experiments 1 and 2 to figure out the rate as it relates to Br-, because BrO3 and H+ stay the same in those 2 trials. So if we're trying to find the exponent m, we would see automatically that BrO3 and H+ cancel out, so we would just compare the 2 rates. So 5 times 10 to the -4th for trial 2, and then 2.5 times 10 to the -4th for trial 1. The K would cancel, the BrO3 would cancel, and the H+ would cancel, so we would just put in 0.002 to the m for trial 2 and 0.001 to the m for trial 1. Divide that and you get that 2 equals 2 to the m power, so the exponent m is 1. Next on our list will be to find the exponent as it relates to our second reactant, BrO3. If we're looking at our data, we want to pick 2 trials where BrO3 changes but the other variables remain the same, and that looks like trials 1 and 3 because the Br- concentration is the same and the H+ concentration is the same. So just like we did for our last exponent, we will compare those 2 trials. Since BrO3 is the only thing changing, we can put just the rate of the third trial on top and the rate of the second trial on bottom, and then we'll compare those 2 reactant concentrations. So that's 0.0075 to the n on top and 0.005 to the n on bottom. You get 1.5 equals 1.5 to the n, so n equals 1. So far so good. We found 2 of our 3 exponents. This should have been pretty similar to what you were doing before. But here's the new part. Notice that if you're trying to find the concentration of H+, in none of these trials does the Br concentration stay the same while the H+ concentration changes. And so for this, you can just pick any 2 trials where the H+ concentration is changing. For example, you wouldn't want to pick 1 and 2 because H+ is staying the same. You wouldn't want to pick 2 and 3 because H+ is staying the same. But you could pick any of the first 3 and compare it to the 4th. So I'm just going to pick the last 2 because, I don't know, we haven't used both those together before, so let's do it. So to find the exponent p, now here is where you have to write out the entire rate concentration reaction and plug in everything that you know, including the concentrations of the other things. So what's bigger? This is to the -3rd, so it's bigger. So we'll put experiment 4 on the top and experiment 3 on the bottom. So 3 times 10 to the -3rd equals K times the Br concentration, which is 0.001 to the first, times the BrO3- concentration, which is 0.015 to the first, times 0.2 to the p power. And then we will divide that by trial 3, which is 3.75 times 10 to the -3rd, K times the concentration of our first reactant to the first, times the concentration of our second reactant, also to the first, times the concentration of our third reactant to the p power. And then you would need to do some algebra, canceling out what you can, see that the k's are going to be the same and the 0.001 is going to be the same. Or you could include that 0.001 in your calculation if you prefer. But when you divide the 2 rates, you get that it's 8 times more. And you compare the concentration of BrO3-, and that's twice as much. And we've also doubled the concentration of H+, and that's to the p power. So 8 times 2 times 2 to the what power? Well, let's get the 2 to the what power on its own. So divide both sides by 2. So you've got 4 equals 2 to the p. That means p has to be 2 because 2 squared is 4. Great, so we figured out our three exponents, n, 2, and 1. Now we're going to have to plug those in and solve for k like we've done before. So let's again write out our rate equals k times br minus to the first times BrO3 minus. By the way, the pluses and minuses do matter. Those are charges on the ions, and those charges must be present in order to have a fully correct answer. So now what we want to do is find the value of k, and for that we can pick any experiment. Let's pick experiment 1. So the rate, 2.5 times 10 to the negative 4th equals k, which we don't know, times 0.001 to the first, times 0.005 to the first, times 0.1 to the second. When you multiply that out, you get 2.5 times 10 to the negative 4th equals 5 times 10 to the negative 7th k. Divide both sides by 5 times 10 to the negative 7th, and the value of k turns out to be 5,000. So we can plug that in. Oh, we also need to find the units on that. If we look at our overall equation, we'll have rate equals k times br minus to the first times BrO3 minus to the first times times H plus squared. That's a 2. So if our overall order is 4, then the units on k will end up being 1 over m to the 4 minus 1, or to the third, times second. So 1 over m cubed seconds. So if we put it all together, we would just replace this number here, the number for k, with 5,000 1 over molarity cubed seconds. That's our value for k. And folks, there you have it. That is advanced rate law calculations. Those aren't too tricky once you practice them a little bit. Please consult your teacher if you have any additional questions. Miss Heaton, signing out.